We also needed to calculate the ratings for our LC filter. Current flowing from the inductor has two parts: the average value of output current, that is DC current, and the AC ripple overriding over the average current, which will be due to the harmonics in my output voltage. This is the DC value, average value, and this is the AC component overriding over this DC value. The average value of output current is equal to 5 ampere, which is equal to the load current. So whatever the value of load current is, the average value of the current from the inductor. And the second one is AC component. AC component is calculated due to the harmonics in my system, and this I am only considering the second harmonic because the rest of the harmonics will be smaller in magnitude, and the current will also be very small due to them. The voltage due to the second harmonic divided by impedance due to second harmonic. The frequency of second harmonic should be twice the fundamental frequency, therefore 2 omega L. IAC P can be calculated as voltage due to second harmonic and divided by its lower value, that is 2 omega L. So the AC component is equal to 0.5 ampere. The average rating of the current will be of current of diode will be the average output value divided by 2, because we have two pairs, and for half time period the one pair will be operating, and for the second half the other pair will be operating. So 5 ampere by 2, the average value of diodes will be 2.5 ampere. Okay, as discussed that the current flowing from the inductor has two parts, DC and AC component, and the same will be flowing from the diodes. Therefore the peak value of diode should be equal to this average value plus this ripple, that is due to the AC component. The height of this AC component is 0.5 ampere, and the average value is 5 ampere. Therefore the peak value of the current from the diodes will be 5.5 ampere. In order to calculate the RMS value of the current flowing from diode, we need to calculate the RMS value of the current flowing from inductor by square root 2, because whatever the value of the RMS value of the current that is flowing from inductor, that is supplied by the two pairs of diode, and in RMS we will divide it by square root 2. We have discussed this formula in capacitive filtering, so either use this approximation or stick to the basic definition, that is integrate for 0 to the conduction time of this diode. When we are using LC filter or inductive filtering, the diode will be operating throughout the half cycle, and the repetition cycle will come after one whole cycle, 20 millisecond. So either use this definition or use this formula, you will get the same result. But at the time being we do not know about the RMS value of the current from this inductor. Okay, in order to calculate the RMS value from the inductor, we know that there are two components. One is the average value, the DC component, which is equal to the load current, and the other one was due to the AC component. And when we have a waveform like this, in which we have a DC component and has some ripple overriding over it, in that case its RMS can be calculated as the square of the average value or the DC component plus this AC component divided by square root 2. Here it is sinusoidal, therefore dividing it by square root 2. If it were triangular, triangular in shape, the ripple, in that case it would have been under root 3, or any other shape, so you will use that factor for in this formula. But here the ripple is AC, therefore we are dividing the peak value of the AC by square root 2, its square and then the square root of the whole term. The current RMS value, the current from the inductor is 5.01 ampere. You need to understand this, that with this AC ripple, this is dependent upon the value of harmonic second harmonic voltage V2H and 2 omega L. In our case the inductance was very high, 2.15 Henry, but in the cases when this inductance will be low, the ripple will be much higher. So in that cases the RMS value will be higher as compared to average value, or we can say that the difference will be more prominent in that case. And this is the current waveform from the transformer. In the case of inductor, 5 ampere was supplied during the positive cycle and 5 ampere was supplied during the negative cycle. Now in the case of LC, it is still the same, but only one thing is added over here, is that there will be some harmonic in it as well, due to the fact that we have been studying till now, that is we have second harmonic, fourth harmonic, up to so on. So this AC component is due to those harmonics, and this is due to that average value. And the RMS value of the current from transformer is equal to RMS value of current from inductor, 5.01 ampere. VS RMS is known. We have calculated this in inductive filtering. So the power factor is 0.899. Power factor is 89.9%, slightly lower than that in the case of inductive filtering, but much higher than the capacitive filtering. So our power factor is good. And the other advantages of using LC filter were that the values of inductor and capacitor are very much reduced. The power factor is good, and an additional thing is that in a setup like this, we have inductor over this side, at this side, input side, and capacitor at the output side. The issues that we were discussing, that it is not suitable, inductive filtering is not suitable for regulated power supply due to the spikes that may appear across this inductor. But here see that we have a capacitor at output, so it will be able to supply or absorb any kind of surges that will appear at across output load. So this is very beneficial for us.